guys, welcome once more to another video on our YouTube channel. So in this video we concentrate on looking at mathematics paper 2 questions of the entrance examination into the National Advanced School of Engineering Yaounde for the 2022 session. So let's get started. This paper was divided into 2 exercises and a problem, and these questions were independent. In this video we are going to be solving just one question, just one of the exercises. In the subsequent videos we are going to solve the second exercise, and in another video we are going to solve the problem. So let's dive straight away into the exercise of this video. So we are going to be looking at exercise 1, which was allocated for 4.5 marks, and it was from the topic numerical sequences. So this topic is very important for all those who want to write concours that are based in French regions. So Polytechnic Douala, Polytechnic Yaounde, Polytechnic Maroua, École des Postes that is Subtic in Yaounde. So this topic is very important for those entrance examinations. This topic tries to relate sequences together with functions, so that is why it is called numerical sequences. Alright, so paying attention to the methodologies and the concepts that will be explained as the video proceeds. Okay, so I'm going to read the questions and then we analyze together and solve. The question read: given u of n a numerical sequence such that u0 is 1, un plus 1 is the square root of 1 plus un minus 1 for all n that belongs to the set of natural numbers. Question 1: given that x lies between 0 and 1 and f of x is equal to the square root of 1 plus x minus 1, we justify that f is derivable and strictly increasing on the interval 0, 1, and then show that for all x in the interval we have 0 less than f prime of x less than or equal to half. Question 2: a, show by recurrence that for all n in the set of natural numbers 0 is less than un plus 1 less than or equal to un less than or equal to 1, 0.5 mark. B, hence deduce that un is convergent and determine its limit. Question 3a, show that for all n we have un plus 1 less than or equal to half un. Question b, hence deduce that for all n we have un less than or equal to half raised to the power n. Question c, determine the natural number n0 such that for all n greater or equal to n0 we have that the absolute value of un is less than 0.001. So this is an exercise, and I would like to first of all give you guys some setting instructions, kind of, alright, or some setting terms. Okay, so when you see natural numbers, you know natural numbers are simply the set of positive whole numbers. Alright, so there is always a little bit of confusion because sometimes we in the Anglophone subsystem we don't consider 0 as a natural number, okay, but the Francophone subsystem considers 0 as a natural number. But nevertheless, in any case, you're always going to be told what this set is actually all about. So you see n belongs to the set of natural numbers. In this case 0 is excluded because you have already been given u0. Alright, so here 0 is included because you have been given u0. So in some cases they will tell you that this n belongs to the set of natural numbers and maybe the n is greater or equal to 1, meaning that you're supposed to begin from 1. In some cases, if they want to exclude 0, they are going to write natural numbers and then they are going to put a star above it showing that 0 is excluded. Alright, so nevertheless, just pay keen to those principles. Now is there any other thing I have to say? There is no other thing. Alright, so let's get straight away to the solution to this question. Alright, so we are going to begin with question 1, which has given us information about a function and an interval where x belongs to, and we are supposed to show 3 things. First, we are supposed to justify that the function f is derivable, and then we justify that it is strictly increasing on this interval, and then we now show that for all x in that interval, our f prime lies between 0 and half, where 0 is excluded and half is included. Alright, so let us begin with justifying that the function f is derivable on the interval 0 to 1. So first of all, showing that a function is derivable on an interval, we just need to show that the domain of definition of its derivative is actually in the interval. So our f was given as the square root of 1 plus x minus 1. So we can get f prime by differentiating the function here. We are just going to get f prime to be 1 divided by 2 times the square root of x plus 1. Alright, now we have that for all x in the interval 0 to 1, this square root here can never be 0, and the square root is well defined, because for the square root to be defined, the interior has to be greater or equal to 0, meaning that 1 plus x must be positive. Okay, but since it is in the denominator, it is not supposed to be 0 because we cannot divide by 0. So the domain of definition of this f prime is that the square root here must be different from 0 and its interior must be greater than 0. Okay, so if the interior is greater than 0, that is for the square root to be defined, and then if the square root is different from 0, then 1 over it has to be defined. That is for 1 divided by the square root being defined, and that simply gives us a domain of definition of f prime. So I will repeat again. F prime is defined if and only if, first of all, the square root is defined and 1 over the square root is defined. For the square root to be defined, the interior has to be greater than or equal to 0. Okay, meaning that you're going to have x greater or equal to negative 1. But all values of x that are greater or equal to negative 1 are already in this interval 0 to 1, and negative 1 is not in that interval, because it is only at negative 1 that makes the interior here to be 0, and the interior is not supposed to be 0 because 1 over it has to be defined, because we cannot be dividing by 0. So we have seen that the square root can never be 0. Okay, so it therefore means that, and it is well defined already in this interval, so it therefore means that the derivative of the function is well defined on that interval. So we can say f is derivable on this interval. Now what about justifying that f is strictly increasing in that interval? Now for all x in that interval, we have seen that our f prime is equal to 1 divided by 2 times the square root of x plus 1. So if a function is strictly increasing in an interval, it means that its first derivative is strictly positive, meaning greater than 0. Okay, so we now need to verify if this function here is greater than 0. Clearly, the square root function is a positive function. Okay, and it can be 0 provided the argument, which is x plus 1, is 0. And for x plus 1 to be 0, x should be negative 1. But in this interval, x cannot take negative 1. So it therefore means that for all x that belongs to the interval 0 to 1, the square root of x plus 1 is always positive. Therefore 2 times the square root will also be positive. Now we can now take the reciprocal on both sides, or in fact, if 2 times the square root of x plus 1 is positive, it means that 1 divided by 2 times the square root of x plus 1 will also be positive, because we are kind of dividing two positive numbers, so it is positive. So this positive means that f prime of x is positive, which therefore means that the function f is strictly increasing for all x that belongs to the interval 0 to 1. Lastly, we have to show that for all x in that interval, our f prime of x lies between 0 and half. So let us begin by showing the upper part, because actually we have already shown that f prime is greater than 0, that is 0 is less than f prime. So if we are able to show that f prime is less than or equal to half, then we can combine the two together and we conclude. So see, having that x is in the interval 0 to 1, it means that x is actually greater than 0, because it is in the interval 0 to 1. So 0 is less than x. Okay, so x is greater than 0. So if we add 1 to both sides, you are going to get x plus 1 is greater or equal to 1. In fact, this is why we are doing this. We are trying to bound f prime of x from above, alright, and to bound a function which is a rational function, we first of all begin with the denominator, and the denominator here is 2 times the square root of x plus 1. So I need to first of all begin with the x plus 1, then I take the square root, then I multiply by 2 before I take the reciprocal. So I begin with what I know, which is x being greater or equal to 0, because it is in the interval 0 to 1. Alright, so I add 1 to both sides, so I get x plus 1. It means I get x plus 1 greater or equal to 0 plus 1. Now x plus 1 greater or equal to 1, it means that x plus 1 is in a positive interval, so we can take the square root on both sides. So the square root of x plus 1 will be greater than the square root of 1, alright, and the square root of 1 is 1. The square root function is an increasing function, okay, it's always increasing. Therefore, if x plus 1 is greater or equal to 1, it means that the square root of x plus 1 will also be greater or equal to the square root of 1. This is because the function is increasing. If the function was decreasing, we are going to switch the bounds, meaning rather we are going to instead have that 1 is greater than the square root of x plus 1. But because the function is increasing, then the inequality sign remains the same. Okay, alright, so from there now, what do we have? We can multiply both sides by 2, and 2 is a positive number, so the inequality sign remains unchanged. So we have 2 times the square root of x plus 1 is greater or equal to 2. We can now take the reciprocal on both sides, and the reciprocal function is a decreasing function. Okay, 1 over is a decreasing function, and since it is decreasing, when you take 1 over the square root of x plus 1, rather the inequality sign is going to change to less than 1 over 2, because that function 1 over is a decreasing function. Alright, so from there the left hand side becomes f prime of x, and the right hand side is simply half. So it therefore means that our f prime of x is less than or equal to half. So we can do the combination of f prime of x being greater than 0 and f prime of x being less than or equal to half to conclude that f prime of x lies between 0 and half for all x in the interval 0 to 1. So we have succeeded in justifying that f is the variable, f is increasing, and then showing that f prime lies between 0 and half. Okay, question 2a. Show by recurrence that for all n belonging to natural numbers, 0 is less than un plus 1, less than or equal to un, less than or equal to 1. So recurrence means that we need to show by mathematical induction. So to show by mathematical induction, we start with our statement. First of all, let's recall that our f of x was given as the square root of 1 plus x minus 1. Our u of n plus 1 is clearly stated as the square root of 1 plus un minus 1. It therefore means that our f of un is equal to un plus 1, because if I replace x with un, I'm going to have the square root of 1 plus un minus 1, which clearly defines un plus 1. Alright, now to prove by mathematical induction, we begin with a statement. Let's say the statement is p of n. It's the statement we are proving, so we need to prove that this statement is true. So there are 4 basic things that we have to do. First, we have to begin with the base case, meaning we have to verify that the statement is true for the very first value of n. And since n is in the state of natural numbers and we have information about u0, it means that we have to verify if the statement p0 is true. P0 being true means we have to verify, we need to replace n with 0, and we have to verify that 0 is less than u1 less than or equal to u0 less than or equal to 1. So we have u0 as 1 already, so this upper part of the inequality is already true, because normally 1 is less than or equal to 1. Now what about u1? u1 can be gotten from replacing n to the 0 in this relationship that relates un plus 1 and un. So u1 is simply equal to 1, the square root of 1 plus u0 minus 1. Then u0 is 1 plus 1 is 2. So we have u1 to be the square root of 2 minus 1. But the square root of 2 minus 1 is actually less than 1, okay? Because in fact the square root of 2 is 1.41. If you subtract 1 from it, it's going to be less than 1. So at the end of the day, we can see that the statement p0 is true, because 0 is less than with 2 minus 1. Because root 2 minus 1 is a positive number, so 0 should be less than it. And the root 2 minus 1 is in 10 less than u0, which is in 10 less than 1, because the u0 in this case is just 1. So we can just combine u0 less than or equal to 1 and we replace it with 1. And at the end of the day, we have that 0 is less than root 2 minus 1 less than or equal to 1, which is always true. So our base case has been verified. Now the next is the induction hypothesis, where we suppose that the statement p of k is true. What does it mean to say that the statement p of k is true? It means that we need to replace n with k, and we have 0 is less than uk plus 1 less than or equal to uk less than or equal to 1. Now we need to now prove that the statement p of k plus 1 is true, which is now called the induction step. So proving that the statement p of k plus 1 is true, therefore means we just need to replace n here with k plus 1. So we actually have to prove that 0 is less than uk plus 2 less than or equal to uk plus 1 less than or equal to 1 after replacing our n with k plus 1. Alright, how do we prove this? First of all, we need to use our induction hypothesis. Always use your induction hypothesis because that is what you have assumed or supposed that is true. So our induction hypothesis says that our 0 is less than uk plus 1 less than or equal to uk less than or equal to 1. Now we have to arrive in this position, meaning we have to arrive where we have 0 is less than or equal to uk plus 2 less than or equal to uk plus 1 less than or equal to 1. So we have to see what we are going to do with this induction hypothesis to arrive at the induction step. If you look closely, you're going to see that this is a numerical sequence, so be very vigilant here. Our f of un is equal to un plus 1. Okay, it therefore means that if I take f all true, if I take f all true, I'm going to have f of 0 is less than f of uk plus 1. I'm taking f of uk plus 1. In fact, I am taking f all true because I have identified that if I take f of uk plus 1, I'm going to get uk plus 2. Okay, because here if you replace n with k plus 1, the right hand side is going to be k plus 2. So f of uk plus 1 will give me uk plus 2. F of uk will give me uk plus 1. So it is already going to the direction where I want. Alright, now when I compose, when I take f all true, I'm going to have this, but this has to be justified because we said that if a function is increasing, then like the function f is increasing, right? The function f is increasing. That is why when you have this inequality, you can take f all true and the inequality signs are going to remain the same. If the function was decreasing, then we are going to switch the bounds. We are going to switch all the bounds. But because the function is increasing, then this inequality sign remain unchanged. So whenever you do this, you have to justify why the inequality sign remain like that. So our justification is that the function f is strictly increasing. Alright, now what is f of 0? Our f of 0 is actually 0. If you compute it here, is a square root of 1 plus 0 minus 1, which is root 1 minus 1, which is 0. Now our f of uk plus 1 is uk plus 2. Our f of uk is uk plus 1, and our f of 1 is simply the square root of 1 plus 1 minus 1, which is the square root of 2 minus 1. But already we saw that the square root of 2 minus 1 is less than or equal to 1. It therefore means that we have proven that 0 is less than or equal to uk plus 2 less than or equal to uk plus 1 less than or equal to 1. Hence the statement p k plus 1 is true. Conclusion: since it is true for n equal to 0, which we saw already, and it is true for n equal to k plus 1 as it is supposed true for n equal to k, then it is true for all n in the set of natural numbers that our 0 is less than un plus 1 less than or equal to un less than or equal to 1, as shown by recurrence or mathematical induction. Okay, question 2b, deduce that un is convergent and determine its limit. So how do we deduce that the sequence is convergent from the previous informations? Let's first of all start by deducing that it is convergent before we determine the limit. So we have recently proved that that 0 is less than un plus 1 less than or equal to un less than or equal to 1. It therefore means that if you consider this portion, right, we have that un plus 1 is less than or equal to un, meaning that un plus 1 minus un is less than or equal to 0. This means that the sequence un is monotonic decreasing. Now we also have that 0 is less than or equal to un plus 1 less than or equal to un less than or equal to 1. It means that the sequence un lies between 0 and 1. Okay, so from here we can see that the sequence un is bounded. Now follow this: if the sequence is increasing and bounded, it converges. Next, if the sequence is decreasing and bounded, it also converges. So it therefore means that this sequence is monotonic decreasing and it is bounded, so it therefore converges. Okay, so that's the conclusion we can make from here, that it's actually a deduction that since it is monotonic decreasing and it is bounded, therefore it converges. Now look at this very well. When I wrote bounded here, I wrote upper bounded. Okay, so if you're increasing and you are upper bounded, you converge, and you definitely converge to your upper bound. But if you're decreasing and you are now lower bounded, you also converge, but you converge to your lower bound. Okay, so it does not mean that it does not mean that whenever you're increasing and you're bounded, you converge. No, you have to be upper bounded and increasing for you to converge, because you might be bounded, you might be upper bounded, but you are decreasing. You don't converge, okay, because you are not lower bounded. So that's why I specified those cases. Nevertheless, in this case, our UN is both upper bounded and lower bounded, because it is between, it is in an interval. So it is lower bounded by 0 and upper bounded by 1, and it is monotonic decreasing. So nevertheless, it converges. Okay, now we have to determine the limit of the sequence UN. So since the sequence is convergent, it means that the limit of UN plus 1 is the same as the limit of UN. So we can say that that limit is L. Now, having that UN plus 1 is the square root of 1 plus UN minus 1, we can take the limit on both sides. Okay, so the limit of UN plus 1 give us the limit of this quantity. We can now replace the limit with L. Remember that this limit here can dive into the square root. The limit of 1 will give you 1. The limit of UN will give you L. The limit of negative 1 will give you negative 1, because it does not depend on n. The limit of UN plus 1 is L. We can now add 1 to both sides of the equation, and then, in fact, we can square both. We can take L plus 1, meaning we send 1 to the left hand side of the equation, and then we square both sides, and then we subtract L plus 1. Alright, so if you add 1, you're going to have on the left hand side L plus 1. If you square both sides, you get L plus 1 all squared to be equal to L plus 1. We can now subtract L plus 1. We factorize L plus 1. From here, you're going to be left with L plus 1 minus 1. Okay, and you're going to be left with L plus 1 times L equal to 0. So this means L is equal to 0 or L is equal to negative 1. Now from here, what are we going to choose? Are we going to choose 0 or negative 1? So we have that the sequence UN is positive. It therefore means that its limit cannot be negative 1, because it is always greater than 0. So you cannot have a negative limit. Therefore we can choose 0 as the limit of UN. Nevertheless, if you look at this very well, okay, we have really seen that if the sequence is lower bounded and it is decreasing, it converges to its lower bound, because this sequence is decreasing and it is lower bounded by 0. It therefore converges to its lower bound. If it was increasing, then it's going to converge to the upper bound, which is 1, because it is upper bounded by 1. But nevertheless, we have seen that UN is decreasing and lower bounded by 0, so it converges to 0, and determine the limit, we still get 0 as our response. So we can conclude that the limit of UN is 0. Okay, next, show that for all n we have that UN plus 1 is less than or equal to half UN. Okay, so first of all, we actually have that UN plus 1 is equal to the square root of UN, the square root of 1 plus UN minus 1. Okay, so what we are going to do is that we are going to rationalize, we are going to multiply the numerator and its denominator of that. We are going to multiply this guy here by the square root of 1 plus UN plus 1. So you see, I multiply it with this quantity and I divide it with the same quantity. It has not changed anything, because you can still divide those two quantities since it cannot be 0. Now let us just multiply the numerators. If you multiply the numerator, you're going to get UN, because you will have this square root times itself just give you what is inside. It's kind of difference of two squares. Okay, and then just multiply, you're going to get UN. Now from there, let's start bounding. We have that U0 is greater than 0. It means that our UN plus UN is greater than 0. It means UN plus 1 will be greater than 1. Okay, so having UN greater than 0 means that UN plus 1 will be greater than 1. That is adding 1 to both sides of the equation. It therefore means that if you take the square root of UN plus 1, you're still going to get that the square root will be greater than 1. So we now add 1 to both sides. You are going to get that the square root of 1 plus UN plus 1 will be greater than 2. Adding 1 to 1 you get 2. Okay, So from there now, we can now take the reciprocal on both sides, and the reciprocal function is a decreasing function, so the inequality sign has to reverse from greater than to less than. Now from there, we can now multiply both sides by un, and since un is a positive, un is positive, so the inequality sign will still remain less than. We multiply the left hand side and the right hand side by un, but the left hand side becomes un plus 1, which is that's actually what we have here, and the right hand side is still this. Okay, so we can introduce the equality. We actually have that un plus 1 is less than or equal to less than half un. It therefore means that un plus 1 is actually less than or equal to half un. I'm going to justify that why we're actually introducing the less than or equal to. First of all, remember that we have to prove that un plus 1 is less than or equal to half un. Okay, but we have arrived at the instant where we have rather that un plus 1 is less than half un. Now, why did I just introduce the equality there? First, we have to know that the statement P or Q is true if and only if any of the statement P or Q is true. Meaning that if P is true, if either of these statements are are true, then the statement P or Q is going to be true. So if P is true and Q is false, we don't have any problem. P or Q will be true. If Q is false, if Q is true and P is false, the statement P or Q will also be true because it is the conjunction, the disjunction, sorry. Alright, so it therefore means that we have seen that un plus 1 is less than or equal to half un. It's already true, right? Because that's what we have. But we know that un plus 1 equal to half un is false. But it does not stop us from saying that un plus 1 less than or equal to half un is true. Okay, it is true already because it is less than or equal to. The less than part is true, but the equal to part is false. So the less than or equal to will be true because it is a disjunction. So we are proving that. Okay, question 3b. Hence deduce that for all n we have that un is less than or equal to half to the n. So we have proven that un plus 1 is less than or equal to half un. So if we divide both sides by un, since it is not equal to 0 and it is positive, then we have that un plus 1 divided by un will be less than or equal to half. We can take some steps behind, meaning that we decrease the, in fact, the ratio between any two consecutive terms of the sequence un will always be less than half. Un and un plus 1 are two consecutive terms. Un and un minus 1 are two consecutive terms. Un minus 1 and un minus 2 are also two consecutive terms. If we decrease till we go to u1 and u0, they are also two consecutive terms. So we have all these equations. So the next thing we are going to do is that we are going to multiply all these inequalities. Okay, so if we multiply the left hand side, all of them, and then we multiply the right hand side, all of them. Now, what can we identify on the left hand side? We see that un is here, so it's going to cancel with this un. Un minus 1 is here, it's going to cancel with un minus 1. Definitely this un minus 2 we cancelled with a certain un minus 2 if we included the next term. And the term before u1 over u0 is simply u2 over u1, so the u1 is going to cancel. So at the end of the day, you are going to be left with un plus 1 divided by u0 on the left hand side. Now on the right hand side, we are multiplying halves. How many times? We are doing it n plus 1 times, because we begin from u0 right up to un, we have n plus 1 terms. Or look at it this way, from u1 to un plus 1, there are n plus 1 terms. So it means that we are multiplying half n plus 1 times. And multiplying half n plus 1 times, we use the law of indices. We just need to add the powers. So we have 1 plus 1 plus 1 plus 1. How many times? N plus 1 times. Now, if we add 1 n plus 1 times, what do we have? We simply have n plus 1. Okay. So it therefore means that the left hand side, which is un plus 1 divided by u0, will be less than or equal to half raised to the power n plus 1. Meaning that we can multiply all through by u0, and our u0 is 1. Then we can decrease now the terms by 1. So un plus 1 less than or equal to half times to the power, half raised to the power n plus 1, because u0 is 1. It means that un will be less than or equal to half raised to the power n, which is what we were required to prove. So we have proven what we are required to prove. Okay, the last question says we should determine the natural number n0 such that for all n greater or equal to n0, we have that the absolute value of un is less than 0.01. So we first of all need to recall that the absolute value of un is equal to un if un is positive, or negative un if un is negative. So in this case, we have that our un is positive. Okay, we had it already since it means that the absolute value of un can be replaced by un. Now let us follow keenly. We have already proven that our un is less than or equal to half raised to the power n, and now we have that un is less than or equal to 0.01. So if we go to the number line and we try to indicate where all these points are, let us say, okay, this is un. Okay, our un has been proven to be less than or equal to less than or equal to half to the n, and then we want to solve for un less than or equal to 0.01. So how then do we relate half to the n and 0.01? So let me just try to place the various cases and you see. So this is un here. Let us say that, okay, this is 0.01. So in this case, you clearly see that our un is less than 0.01. Now un is also less than half to the n. So half to the n could be here. You see here our un is less than half to the n, as well as it is less than 0.01, or half to the n could still be here. So you see that our half to the n could be here, and you see that un is less than the half to the n, and it is less than 0.01 at the same time. Okay, and as well it is less than it is less than half to the n if half to the n is placed here. So in a nutshell, if un is less than or equal to half to the n and un is less than 0.01, it means that our half to the n could be less than 0.01, or it could be greater than 0.01 because it is placed in two different positions. Half to the n could be placed here or could be placed here. Okay, so these two things means that our half to the n could be either less than 0.01 or could be greater than 0.001. all right, so let's take the first case where we have half to the n greater than 0.001. From there, if we take ln on both sides, okay, we are going to get, we drop the power, we have n ln half greater than 0.01. So from there, ln half is negative, ln 0.01 is also negative. So if we divide both sides by the negative sign, the negative ln half, divide both sides by ln half, since ln half is negative, the inequality sign will change to less than. Ln 0.001 is negative, so the negative signs are going to annul. So we get n less than 9.97. But since n is a natural number, it means we can say that n less than 9.97 means that n is less than or equal to 9. Okay, because it is natural number, and we need to take all natural numbers that are less than 9.97, means we have to begin from 9. So we have to include 9. Now let's take the second case where we have half to the n now less than 0.01. We can say take ln on both sides, and then at the end of the day, if we do the same manipulations, we are going to get that n will be greater than 9.97. But since n is a natural number, we need to take all natural numbers that are greater than 9.97. It means we can begin from 10. So n greater than 9.97 means that n is greater or equal to 10, since n is a natural number. Now what is n0? Now we need n to be greater or equal to n0. Okay, and if you see the first case, our n is less than or equal to 9, so 9 can never be n0. So n greater or equal to 10, it kind of relates with n greater or equal to n0. So it means that our n0 is equal to 10, because we have seen that n greater or equal to 10 coincides with, if you compare n greater or equal to n0 with n greater or equal to 10, it means that our n0 is equal to 10. So that's the value of n0. Alright, thank you guys for watching. We have come to the end of this video. Check out exercise 2 and also the problem. Subscribe to the channel, turn on your notifications so that when exercise 2 will be uploaded, you will be notified to come and watch. Do well to like the video, comment in the comment section, share the video with your friends who are also preparing for the concours, be it Polytechnic Douala, be it Polytechnic Marwa, be it Subtic, or any concours which is based in the French region. This video is for you guys. Thank you once more, and see you in the next video.